In this video, we're going to talk about simplifying radicals. We're going to start with square roots. To simplify a square root, which is what I want to do here, I want to take out the biggest perfect square. I don't want to have any perfect square factors inside of the square root. So I'm going to take out the biggest perfect square factor. And that way I don't have any perfect square factors inside of the root left. So I'm going to start with number 1. I have the square root of 24. I can break this down to be, well, the biggest perfect square inside of 24 is 4. So I can rewrite this as the square root of 4 times the square root of 6. I just broke down what was inside into 2 factors. 4 times 6 gives me 24. I'm breaking it down, and the reason why I did that is because now I have the square root of 4, which I know is a whole number. If I have a perfect square, the square root of it is going to be a whole number. So I can change this to be 2 times the square root of 6, and then I just write that as 2 square roots of 6. And this is the simplified version of that square root. For number 2, I have the square root of 242. This might take some playing around to figure out, but the biggest perfect square inside of 242 is the square root of 121. Square root of 121, that's half of 242. So I have the square root of 121 times the square root of 2 gives me the square root of 242. I know that the reason why I took out the biggest perfect square is because I know that's a whole number if I take the square root of a perfect square. And what gets me 121 when I multiply it by itself? That's 11. So the square root of 121 is 11. I have 11 times the square root of 2, which is 11 square roots of 2. For number 3, I have the square root of 300 x to the 4th power y to the 7th power. Here before I just had constants to deal with. Now I have some variables in there as well. This is 3 different types of factors inside. So I have my constants, or just regular numbers, I have my x's, and I have my y's, and I'm going to have to look at all of them separately. So looking at my constants, or my numbers, my regular numbers, I have 300. So I really have the square root of 300, and that breaks down into, I'm just going to write this, square root of 300, I have the square root of x to the 4th power, and I have the square root of y to the 7th power being multiplied together. To break down the square root of 300, I can break that down into the square root of, the biggest perfect square that's inside of 300 is 100. So I could break it down into the square root of 100 times the square root of 3. 3 times 100 gives me 300. For x to the 4th power, to have a perfect square with a variable raised to a power, that power needs to be even. If I take the square root of x to the 4th power, I'm going to get a variable raised to a power, and I'm going to be able to get rid of the square root. So this is, I'm just going to leave as the square root of x to the 4th power, and then for y to the 7th power, the biggest perfect square inside of that is, because this is an odd power, I need the even power less than that. So I can break this down into the square root of y to the 6th power times the square root of y. So all of these are being multiplied together. I'm going to bring all my perfect squares to the front. So I have the square root of 100 times the square root of x to the 4th power times the square root of y to the 6th power. And then at the end, I'm going to put my square roots that are going to stay square roots because there's nothing perfect inside of them. So I have 3 and, I'm actually going to... the square root of 3 times the square root of y. All of these are being multiplied together. From here, I'm just going to simplify what I have as the perfect squares. So the square root of 100 is 10. The square root of x to the 4th power is x to the 2nd power. The square root of y to the 6th power is y to the 3rd power. And you can, if this is confusing you, this is actually y to the 6 divided by 2 power, because I'm raising it to the 6th power, and then I'm taking the square root, and then that simplifies to 3, the power being 3. And then I have the square root of 3 times the square root of y. I can collect that as the square root of 3y. And this is my final answer. For number 4, I have some similar to the last problem, except the first thing I want to do here is combine my roots and combine my constants on the outside, or my coefficients. So I'm going to multiply what's on the outside, 3 times 2, and then I'm going to multiply what's inside it together. So I'm going to have 3 times 2 times the square root of, I have 2 times 6, which is 12, x times x to the 4th power, which is x to the 5th power, and y squared times y, which is y cubed. From here, I know that I have, this is 6 times the square root of 12x to the 5th power y cubed. What I'm going to do here is inside of the square root, I'm going to look at my constants, my x's, and my y's separately from each other. I'm going to have 6 times, I want the biggest perfect square inside of all of these factors. The biggest perfect square inside of 12 is 4, so I break it down into the square root of 4 times the square root of 3. And then for that x to the 5th power, the biggest perfect square inside of there is x to the 4th power, so I rewrite it as the square root of x to the 4th power times the square root of x. And then for y, I have that is the biggest perfect square inside of y cubed is y squared, so I rewrite it as the square root of y squared times the square root of y. So all of these things are being multiplied together. I want to rewrite all my perfect squares or whole numbers in the front. So I have 6 times the square root of 4 times the square root of x to the 4th power times the square root of y squared. And at the end, I'm going to put all my things that remain in the square root. So I'm going to have a square root of 3 times the square root of x times the square root of y. And then I'm going to simplify. So I have 6 times 2 times x squared times y. This is what I'm multiplying together, times all of these square roots I can collect into one. So I'm going to do that, 3xy inside of a square root. And then I just simplify again. I have 12x squared y times the square root of 3xy. All right, next we're going to talk about nth roots. So I want to break down what's inside into its smallest factors. So I want to break down what's inside to its smallest factors, and then I want to take out groups of n of the same factor. That's what I do when I have nth roots. So nth roots is different than if I have square roots. All of these were square roots. So nth roots just means like roots that are more than 2. So 3, 4, 5, etc. For number 5, I have a cubed root. So I have the third root of all of this that's inside. And to simplify that, I want to break down everything that's inside into its smallest factors, and then I want to take out groups of 3. So n in this case is 3. The nth root here is the third root, n is 3. So what I'm going to do on the side here is to break down 28 into its smallest prime factors. I'm going to use one of those factor trees. So I have 48 breaks down into 2 times 24, and 24 breaks down into 2 times 12, and 12 breaks down into 2 times 6, and 6 breaks down into 2 times 3, and that's as far as I can go. So I have 1, 2, 3, 4 2s, and 1 3 being multiplied. So I'm going to rewrite what's inside here as the cubed root of, I have 2 times 2 times 2 times 2 times 3 for my 48. And then for the x's, I have 3 x's being multiplied together, 1, 2, 3. And for my y's, I have 6 y's being multiplied together, 1, 2, 3, 4, 5, 6. Now I want to take out groups of n, groups of 3. So I'm taking out for the constants a group of 3 2's. This is a group of n, or a group of 3, since n is 3 in this case. And then I'm going to circle I don't have any other groups of 3 for the numbers. Then I'm going to go to my x's. Oh, I have a group of 3. So another group of 3. And then for my y's, I have 1 group of 3, 2 groups of 3. So groups of 3. Groups of 3. And when I take out the groups of 3, I know the cubed root of 2 times 2 times 2 is 2. I know the cubed root of x times x times x is x. And the cubed root of y times y is y. Because what do I have to multiply by itself 3 times? To get y times y times y, I have to multiply y by itself 3 times. And then I have 2 y's there being multiplied since I have 2 groups of 3 y's. So I'm multiplying these together, and then I'm multiplying the cubed root of everything that's left inside that I didn't circle. That's just 2 times 3, which is 6. I didn't need a super long thing. And then I just simplify by multiplying the y's together, consolidating the y's. So I have 2xy squared times the cubed root of 6. For number 6, I want to break this down into its smallest factors. So I'm going to rewrite this cubed root as the cubed root of, I have negative 27 is, I can break it down into negative 3 times negative 3 times negative 3. X, I have 3 x's there, 1, 2, 3 x's, and 6 y's, 1, 2, 3, 4, 5, 6. And you don't have to do this way if you don't want to. If it's easier for you to just do what we did with the square root, and then just think about it as the cubed root instead, you can do that, like taking out the biggest perfect cube. Alright, I'm circling groups of 3. I have a group of 3 negative 3's. I have a group of 3 x's, and I have 2 groups of 3 y's. And so when I take all those things out, that's everything inside. I'm going to end up with negative 3 on the outside. The cubed root of negative 3 cubed is negative 3. And then I have 3 x's, so I have an x on the outside, and 2 y's being multiplied together. All these things are being multiplied together, and to simplify, I just bring my y's together to be y squared, and this is my answer. For 7, I have the 5th root of 4x squared divided by the 5th root of x. The first thing I want to do, if I have the same root on top as I do on the bottom, I can consolidate and simplify what's inside. So I can say this is the 5th root of 4x squared divided by x. And then that's like the opposite of distributing. And then I can simplify what's inside. So I can rewrite this as the 5th root of, 4x squared divided by x is 4x. I can't simplify any further than that. That's my final answer. For number 8, I have the same situation with I have the same root on the top and the bottom. So I can simplify this to be the 4th root of 80y to the 7th power divided by 5y squared. And then I'm going to just simplify what's inside of that 4th root. So I have the 4th root of 80 divided by 5 is, 40 divided by 5 is 8. So 80 divided by 5 will be 16. I have 16, and then y to the 7th power divided by y to the 2nd power is y to the 5th power. And now what I want to do is I want to break down what's inside of here to its smallest factors. There was nothing I could break down for into that there were 5 factors being multiplied together. And there's only 1 x here, so there's not 5 x's for me to take out. So that's how I knew that was all I could do. But here I do have 4 y's, and I will have a group of 4 y's, and I can break down 16 into 4 factors. So if I, on the side, break down 16, I have 2 times 8, 2 times 4, 2 times 2. I have 1, 2, 3, 4 2's being multiplied together. So I can rewrite this as the 4th root of 2 times 2 times 2 times 2. And I have 5 y's. 1, 2, 3, 4, 5. And then I know I have, oh wait, I can't take out any 2. Oh wait, I can. Sorry, I was thinking it was a group of 5. Okay, so I have 4 2s I can take out and 4 y's I can take out. And so I'm going to have on the outside the 4th root of 16, or 2 times 2 times 2 times 2, or 2 to the 4th power is 2. And then the 4th root of y to the 4th power is y. And then what I will have left inside is the 4th root of y. And this is as simple as I can make it. All right, adding radicals together. So for me to be able to add 2 radicals together, they have to have the same radical. They have to have the same square root. So I need to turn them into like terms if they are not already like terms. And then after I do that, I can combine them. So for this first one, I have the square root of 27 and the square root of 12. Those do not go together, but maybe if I simplify, I can get them to be the same thing, or like terms. So if I break down because 27 I know has a perfect square inside of it, and so does 12. So if I break down 27 into a perfect square times if I break down 27 and I take out its biggest perfect square, I'll have 2 times the square root of 9 is its biggest perfect square, times the square root of 3. So that's how I can rewrite that first term. And then the second term, I have 5 square roots of 12. I can rewrite this as 5 times the biggest perfect square inside of the square root of 12 is 4, so the square root of 4 times the square root of 3. So this is being multiplied together. And then I know that I can rewrite this as 2 times 3 times the square root of 3. So 2 times 3 times the square root of 3, and this is 5 times 2 times the square root of 3 that I'm multiplying together. And that's going to give me 6 square roots of 3 minus 10 square roots of 3, which is negative 4 square roots of 3 if I combine. So I have 6 square roots of 3 minus 10 square roots of 3, that's negative 4 square roots of 3. For 10, I have, I'm going to do the same thing. These are not the same, but I know 48 has a lot of factors I could break it up into, and so does 243. So I'm going to see if I can take out groups of 4 with both of them. Once I find the prime factorization, I'm going to do my trees on the side. So I'm going to do, for the first one, 48 breaks down into 2 times 24, 2 times 12, 2 times 6, 2 times 3, and I have 4 2's being multiplied together. So 1, 2, 3, 4 2's being multiplied together, and a 3, and then that 2 on the outside I don't want to forget about. And then for the second term, I have 243 breaks down into 3 and 81. And then 81 breaks down into 9 times 9, which breaks down into 3 times 3, and 3 times 3, and I have a total of 5 3's being multiplied together. So I have the 4th root of 3 times 3 times 3 times 3 times 3, and that's being multiplied by 3. And then I know that I can take out 4 2's here and 4 3's here. So I can rewrite the left term as 2 times 2 times the 4th root of 3. It's all being multiplied together. Plus I have the second term, 3 times 3 from the inside. The 4th root of 3 to the 4th power is 3. And then what's left inside is the 4th root of 3. So I'm multiplying these together. And then I have 4 4th roots of 3 plus 9 4th roots of 3 for a total of 13 4th roots of 3. And this is my answer. All right, for the next section, I'm multiplying radical expressions. When I multiply radical expressions, I'm going to use my area square because it makes my life easier. So I'm going to use my area square. I'm going to put the left factor here On the left, the square root of 10 minus 6, I'm going to break it up. And then I'm going to put the square root of 10 and 6 as the other side length on the top. The square root of 10 times the square root of 10. If I do this off to the side, the square root of 10 times the square root of 10. This is the square root of 10 squared, or the square root of 100 if I combine it, and that is 10. It's going to be 10. So I know this is 10. This is 6 square roots of 10. This is negative 6 square roots of 10, and 6 times negative 6 is negative 36. This and this, if I add them together, it equals 0, so I can cancel those out. I have 10 minus 36, which is negative 26, is my answer. For number 12, I have the same thing. I'm going to set up my area square. I'm going to do, on the left, I have 5 square roots of 3 plus the square root of 2. And on the top, I have 5 square roots of 3 and negative square root of 2. And off to the side, I'm going to do 5 square roots of 3 times 5 square roots of 3. When I combine this, I combine my constants on the outside. That's 25. I combine my two radicals together, my square roots together. That's the square root of 9, which is 3. So I have 25 times 3, which is 75. So this is 75. I have if I multiply 5 square roots of 3 times negative square root of 2, that's negative 5 square roots of 6. I multiply what's inside of my square roots together. For 5 square roots of 3 times the square root of 2, I have 5 square roots of 6. And then for negative square root of 2 times square root of 2, I have negative square root of 2 times square root of 2 is the square root of 2 squared. For the square root of 2 times 2, groups of 2 coming out, this is 2. So it's negative 2. And I know that if I add 5 square roots of 6 and negative 5 square roots of 6, that equals 0. So I just have 75 minus 2, which is 73, is my answer. All right, on the next page, I have simplifying exponentials. So when I simplify exponentials, I want to combine the like terms. Before we go into that, I'm going to talk about the things that you need to know if you forget them. If I multiply x to the m power times x to the n power, I know that that means I have x to the m plus n power. If I divide two bases with powers, I know I'm going to subtract their powers. So if I have x to the m power divided by x to the n power, it's x to the m minus n. For x to the m to the n power, if I have a power to a power, I multiply. We did the slash unit. I multiply, so I have x to the mn power. If I have, in parentheses, two different factors being raised to a power, I need to distribute that power to both of the factors or all of the factors inside the parentheses. So I have x to the m power, y to the m power. And then for the last one, I have x to the negative m power is equal to, if I have a negative exponent, to change it to a positive exponent, I move it to, if it was in the numerator, I move it to the denominator. So I just do the reciprocal and make the power positive. So I have 1 over x to the m power. So same if you had 1 over x to the negative m power, this would be equal to x to the m power. So two separate things, but they are the same concept. All right, so let's do number 13. So for 13, I want to, when I combine things and multiplying things together, I'm combining all my factors that are similar. So if I have constants, I'm bringing those together, and if I have x's or any other variable, I'm bringing those together if they're the same. So 3 times 4 gives me 12, I know. X to the 1/2 power times x to the 2/3 power. I know that I'll be adding those powers together. That's my first property here. So I'm adding those powers together. I have 1/2 plus 2/3. The base needs to be the same for me to add fractions together. So I'm going to change the base to 6. 1/2 I'm going to write as 3/6, and 2/3 I'm going to write as 4/6. And when I add them together, I have 7/6. So I can't say that. I have x to the 7/6 power times 12. This is my answer. All right, for number 14, I have some things in parentheses raised to a power. I need to distribute that power to both different factors. So I have 2 being raised to the 3rd power, and I have a being raised, say a to the 1/4 power being raised to the 3rd power as well. And so to do the 3rd power is 8. 8 to the 1/4 power raised to the 3rd power. I'm multiplying these things together. 1/4 times 3/1 gives me 3/4. So that's a to the 3/4 power. For number 15, I have 2x to the 2/5 power times 6x to the 1/4 power. I'm bringing my constants together. So 2 times 6 gives me 12. I'm bringing my x's together. So I have x to the 2/5 times x to the 1/4. I know I'm adding the powers together when I multiply 2 things with the same base. So I have 2/5 plus 1/4. I need the denominator to be the same, so I'm going to change the denominator to be 20, because that's what 5 and 4 multiply to be. And it's also the least common multiple. So I have 20. That means I'm multiplying this one by 4. So I'll have 8/20ths, and then this one I'm multiplying by 5/5, and that means I'll have 5/20ths, and add those together, I have 13/20. So I have, my final answer is 12 times x to the 13/20 power. For number 16, I have 9x to the 4th power, y to the -2nd power raised to the 1/2 power. I'm going to distribute this 1/2 to every different type of factor inside. I'm going to have 9 to the 1/2 power times x to the 4th power raised to the 1/2 power times y to the -2nd power raised to the 1/2 power. And I'm going to simplify all this. So 9 to the 1/2 power, that's the same thing as the square root of 9. I didn't need to write that. Square root of 9. I have my x to the 4th power raised to the 1/2 power is x to the 4 divided by 2 power, and y to the -2nd, so -2 times 1/2 gives me y to the -1st power, and then I rewrite this to simplify it. I have 3x squared, and this I rewrite as, using this, I rewrite as 1 over y to the 1st power. And this is my answer. Okay, and then for the next few problems, I'm going to write each expression in exponential form. So instead of writing it as a root, we did this last unit, I'm going to write it, instead of writing it like this, I'm going to write x to the m, what I'm raising it to, divided by n power. The root is what I have in my denominator in the exponent. And what I'm raising it to is the numerator. And so I'm just going to rewrite these really easy. X to the 3rd power, taking the square root of that, is x to the 3 divided by 2 power. So I took this root and I made it the denominator, and that's it. Done. For 18, I have the cubed root of 2y squared, so I'm just going to do 2y squared raised to the 1/3 power. So I know I was raising this all to the 1/1 power and taking the 3rd root. So raising it to the 1st power and taking the 3rd root. So that 3 in the denominator comes from that root of 3. For 19, I'm going to write what's inside 3x cubed y squared. And I'm raising that to the 1/4 power. So I saw the 4th root, that becomes the 1/4 power. And then for 20, I have everything inside, 9x cubed, y to the 5th power. That's being, and I have 4 on the outside. That's being multiplied, not the root. This is what's being multiplied. If it was a root, it would be here. And this is just the square root then. This is just the square root. So that is the same thing as the 1/2 power. And this is my answer. All right, and then lastly, rationalizing the denominator. So by multiplying by whatever, I'm going to rationalize the denominator if it's just a single square root or nth root. I'm just going to do multiply by whatever will cancel the base root. Whatever will cancel the base root, whether that be the square root or the nth root, the cubed root, the fourth root. So in this 21, I want to multiply by the denominator, the square root of y, because then I'll have, if I do off to the side, the square root of y times the square root of y, that's the square root of y squared, and the square root cancels out that squared. I really have two y's being multiplied together. I'm taking out groups of 2, if you want to think about it that way instead. But it's going to get rid of the square root in the bottom. So you can't have a root in the bottom, basically, is what rationalizing the denominator is doing. You're not allowed to have a square root in the bottom, just like you were not allowed to have an imaginary number in the bottom. When we rationalized, or we fixed the bottom of a fraction before. So I have the square root of 6x times the square root of y in the numerator. That's the square root of 6xy. And then in the denominator, we did this off to the side. This is equal to y. And that's my answer. For 22, this is a little bit different because I have the nth root here, not the square root. So I need to have groups of 3, not groups of 2 inside. I know I'm going to have to multiply by the cubed root of something. The cubed root of something in the top and the bottom. And in this case, I only have 1, 2. That's a prime number, so it's the smallest I can make. So I want to multiply by, I want a group of 3, so I want to multiply by 2 more 2's. So I want to have a total of 3 2's when I multiply. I also want to have, I only have 1 a here. I want to have 2 more a's. So for a total of 3. So I want to multiply by a times a. So I want to multiply the top by the same thing. You have to multiply by a giant 1, something the same in the top and the bottom. So here I'm going to have, in the numerator, I'm going to have the cubed root of 5 times 2 times 2 times a. And in the denominator, I'm going to have the cubed root of, I have 2, 2, 2, and a. Aha. That is 3 2's and 3 a's. And when I rewrite the bottom, let's rewrite the top first. I have the cubed root of, that's 10 times 2, which is 20 a squared, and there's no groups I can take out of there, so that stays the cubed root of that. Then in the bottom, I have the cubed root of 2 cubed is 2, and the cubed root of a cubed is a. So this is my final answer. Now you notice there is, in the denominator, no cubed root. For 23 and 24, sometimes I'm going to have an expression in the bottom with addition or subtraction. And if I have that, and not just a root by itself, I'm going to have to do the same thing I did with the imaginary numbers in the bottom. I'm going to multiply by the conjugate of the base. So multiply by the conjugate of the base. And if you forget what conjugate is, it's if I had a plus bi, the conjugate would have been a minus bi. I just changed the sign in the middle. So in this case, if I have a plus the square root of b, it would be a minus the square root of b. That would be the conjugate. If this is the original, this would be the conjugate. And so for number 23, I'm going to multiply by the conjugate of the base. So I'm just changing this sign. I'm going to multiply by 2 minus the square root of 3 in the top and the bottom. Now I'm going to do the top. So the top is going to be 5 times 2 minus the square root of 3. That I just distribute this 5 to both terms, I'm going to have 10 minus 5 square roots of 3. And that's going to be the top. The bottom, now, I have 2 plus the square root of 3 times 2 minus the square root of 3. At some point, you should be able to realize this is the difference of two squares and bring them together that way, but if you want to FOIL it instead, you can. I'm going to FOIL it just to FOIL it. I have 2 times 2, which gives me 4. I have 2 times the square root of, the negative square root of 3, which is negative 2 square roots of 3. I have the square root of 3 times 2, which is positive 2 square roots of 3. And then the square root of 3 times negative square root of 3, which is minus 3. And then I have 4, this cancels out, minus 3, which is 1. The answer then, I don't need to include in the denominator. I have 10 minus 5 square root of 3 in the numerator. I don't need to include the denominator if it's 1, so my answer is just that. For 24, I have 1 plus the square root of 5 divided by 1 minus the square root of 5. I'm multiplying by the conjugate of this. So multiply by, 1 plus the square root of 5 over 1 plus the square root of 5. And then I'm going to do the top first. Whoopsies. Not enough space. I'm going to do the top first. So I have 1 plus the square root of 5 times 1 plus the square root of 5. I'm going to FOIL this. So I have 1 times 1 is 1. 1 times the square root of 5 is the square root of 5. The square root of 5 times 1 is the square root of 5. And then I have the square root of, the square root of 5 times the square root of 5, which is 5. And when I add this together, I have 1 plus 2 square roots of 5 plus 5. I collect my numbers together, my constants together. I have 6 plus 2 square roots of 5, and that's going to be my numerator. The bottom is going to be, I have 1 minus the square root of 5 times 1 plus the square root of 5. This is the difference of two squares. So I should have 1 squared minus the square root of 5 squared, and you can FOIL this if you want to, but that's 1 minus 5, which is negative 4. That's my bottom. And then the answer is going to be, I have 6 plus 2 square roots of 5 over negative 4. I see that all of these terms have something in common, so I also have to take out what they have in common. They have a 2 in common, so I can take out a 2 in the top and a 2 in the bottom. That will cancel. 2 times 3 gives me 6. 2 times the square root of 5 gives me 2 square roots of 5. And then at the bottom I have 2 times negative 2 gives me negative 4. So my final answer is 3 plus the square root of 5 divided by negative 2, and that's it.